Okay, let's get started. Hi, everyone. Thank you all for joining us for another Always AI Developer Hacky Hour. My name is Lizzie Alves. I'm part of the marketing team here at Always AI, and I'm super excited to be hosting today's Hacky Hour. Hacky Hour is an event that is designed for our community to share new product releases, do code demos, and have engaging exercises in an interactive format. We will continue to host Hacky Hours on a monthly basis when we have new product releases to share with our Always AI community. Feel free to utilize the chat window or raise your hand throughout the presentation to ask questions, and we'll be happy to answer them as promptly as we can. If you're joining us for the first time and you're new to Always AI, please make sure that you visit alwaysai.co and sign up for a free account to start your computer vision journey. We have a very special Hacky Hour in store for you today. We're going to be covering NVIDIA CUDA, contours, background subtraction, and color spacing. Now I'm going to hand it over to our co-founder and CTO, Steve Griset, and he's going to kick things off. Steve?
Oh, thank you, Lizzie. So let's go ahead and get started on the slide deck here and move down. So first of all, we sometimes forget that with all the machine learning around, that computer vision itself in the classical form can be used to do many different things without using expensive machine learning algorithms and so forth. And we're going to explore some of that today. Now, as you're working away and doing these computer vision algorithms and so forth, you can also offload it to a GPU through the CUDA interface, the same as you do when you're doing machine learning algorithms. And then on the other side, if you machine learning algorithms like detectors and so forth, you get a return value where you can get a bounding box and other information about the object. Well, when you're using the traditional ones, you don't have that type of situation. So contours are an excellent way to gain insights on what's going on the object and so forth. And we'll explore that today too, as we couple those. So let's go to the next slide on this. So today we're going to be working on two different hardware devices that are all really good devices to use to bring project to production. So there's the Raspberry Pi 4, and the one we're going to be using has 4 gigs of memory. And of course, you have a 4-core CPU that's running at 1.5 gigahertz. The other interesting thing is we all know that community and everything about Raspberry Pi, but if you go to their site and so forth, there's the industrial side where you can get compute modules and boards and so forth, where you can build out production quality computer vision products. So it's a really good product to prototype and use. And of course, we support it here at Always AI. On the right side over here, we have, can we go back for a second? On the right side, we have the Jetson Nano and the B01 developer kit here. Now, the Jetson has the exact same specs as the Raspberry Pi 4. So it's got 4 gigs of memory. It's got the 1.5 gigahertz 4-core system, but it also has a GPU that allows you to execute either computer vision algorithms or machine learning rhythms on. So the key point is here, I think I want to say, is you can get an extra little oomph on your applications using the Jetson Nano. And by the way, if you don't use CUDA and so forth, what you basically have is a Raspberry Pi. So we're going to show you today how to get more out of that Jetson Nano. So next slide, please. So the way we're going to be using CUDA today, which is the software stack from NVIDIA and how you access the GPU, we're going to be using OpenCV. And OpenCV, since 2018, has been, for traditional computer vision, has opened itself up to the CUDA backend. So it has code that will work again using CUDA to drive the algorithms onto the GPU. Now, one thing I want to talk about is, how does CUDA get its speed? How does it do parallelism? So what it does is data parallelism. And so the way I like to visualize that, let's think of a matrix, right? And we want to multiply each element with a scalar of that matrix. So how it parallelizes data is you come in and each element of that matrix is multiplied in the GPU and rounded and done all those types of things all at once for each element at it. So that's how you get data parallelization, which is different from task parallelization, which is where like I have my 4 cores and I want to put one process on one process on another and work the system that way, or have a threading model where I put one thread on one core and so forth. So it's a little bit different than task parallelism, it's data parallelism. And the reason that's important, well, think about where we use a lot of matrix, a lot of multivariable calculus and everything else like that. Well, we use that in traditional computer vision algorithms, but we also use that in machine learning and so forth. So that's why the GPU with its data parallelism is ideal situation for us here in computer vision. So next slide, please. All right, so let's talk a little bit about CUDA nomenclature. So CUDA, you think of CUDA works in units of work called kernels. And what is a kernel? Well, a kernel is a CUDA C extension. And what that extension allows you to do is as you're executing something to get that data parallelism, it kicks off an amount of threads. So how many elements I have, I get that many threads going down and working within the system. So that's working within the GPU system. So that's what CUDA does on extension. And you call that unit of work or so forth that goes on a CUDA kernel. Now, to get some more concurrency and asynchronous, there's another concept called a CUDA stream. And a CUDA stream lets you run things concurrently, and then it also lets you allow different things and to run them interleaved and so forth. So you get your concurrency, you get your heavily parallelized data calculation through kernels, and you get your asynchronous ability between using something called streams. The other thing I want to talk about is just a naming convention. And as you work in CUDA and as you work with GPUs and so forth, you're going to hear people talk about the host. And the way I like to think about it in a very simplistic manner is the host is just simply the CPU and the device is the GPU. And if you're working in a cluster, you may have more than one device to access, but on a standard Jetson product that we're working with today, there is only one device. So it's host to device. So think of it that way. Next slide. So let's get to work. Let's demo some code and talk about code, which is why we're all here. So the first thing we're going to do is have me share my screen so you know what I'm talking about. And let me go ahead and hopefully I'm going to ask you, Lizzie, whether you see the screen or not on my desktop. Do you see the desktop, Lizzie?
Yep, I see the desktop.
And we're good to go. So so basically what we're going to do is download the application. So if we come here into our GitHub site, you can see we have lots of stuff. We have a complete reference application site where you can go through and see different things you want to do. In computer vision, there's a lot of example code and a lot of good content up here. We're going to look specifically today for our system, which is CUDA and contours. So we're going to go grab that. And we're going to go ahead and we're going to clone this down into a repo. So I'm going to bring up my system. I'll go ahead and make sure that I make it a little larger so people can see it. And I'm going to go ahead and go put my code into a subdirectory called Hacky. And I'm going to do a git clone here and just paste in what I have. And this is all you need to do to get the code that we're using today. Takes just a little bit of time, but not too much. And yeah, well, let's let it finish up its last thing. Little integrity check there. Come on. And boom, there we go on that. So now as you can see, if we go in, we're going to have like CUDA and contour subdirectory in there, and then you'll list out, we'll have our 2 application subdirectories that we're going to be working with. So the first one we want to take a look at is color spacing. And we're going to go into the color spacing subdirectory here. And first of all, what is color spacing? Color spacing is a way to consistently represent colors in an application. And the color space that we are most aware of is something called red, green, blue. And so you see that all the time, and it's the 3 primary colors and so forth, and we use those to build other colors around. We're going to be in this application getting a video stream in RGB, and in real time, we're going to be changing it over to 4 other color streams, one called HSV, one called YCC, and the other called Lab. We're not going to get into details of color spacing. We have some earlier hackathons that do that, but what we want to do is see what the speed difference is running on a CPU versus a GPU. That's the main demonstration of this application. So let's go ahead, and just so you get a concept of what we're going to do, we'll go ahead and get this set up to run on the Raspberry Pi, and then we'll take a look harder at the code. But first, just to get an idea of what's going on, let's get that started. So the first thing we have to do is use our CLI, alwaysAI app, and we want to configure the application. So we're going to come in and we're going to create a project, and I'm simply just going to call this Hacky CS for color spacing, and we'll do that. I already have an application. If you want to get one of our starter apps, you can go there. If you're working from a Git, you can go there. I have the application. You saw I downloaded it from Git, so it's there. So I'm going to do an empty app and let it see. It's going to find my app there. I want to go ahead and choose my remote device. If I didn't have it set up, I'd also go through a setup process here, but because I don't want you to have to go through the setup process during this demo, I already have it done. So I'm going to go down and go to my Raspberry Pi 4. And it's going to hopefully connect up. There we go. It's updating security tokens. It's checking all my Docker permissions. And if you stumble in one of these areas, you just go to the documentation. It'll show you how to set up your Docker permissions, how to set up Docker on your Raspberry Pi, and so forth. So I'm going to choose where I want to put that. And so forth. So now I'm all configured and set up. And if I went to our dashboard system, you would see this project in my dashboard. Let's go ahead now. And then what we're going to do as part of the development process, we're going to install that application onto the device. And we're going to go do that. And part of that installation will bring down a Docker image. So you may see a lot of pulls and so forth that this is your first time running it. It's going to take a little bit of time. It's going to bring down that image. We have everything in alwaysAI in Docker containers. So it's all set up for you, all the middleware, everything else. You don't have to worry about it, but it does take time to get it down. And you can see we're going to be using 1.50, which was released today on the Edge IQ system, which is our software system. So the last thing we're going to do, we've all done all this neat stuff, and we're going to go ahead and just start the application. And sure it's going to start after all that. And here we go. And what I want to do is show you the application. So here comes the application. It's Usain Bolt, like beating everybody as usual. And what we can see right here is we have, our RGB color space. In case of OpenCV, it's actually a BGR. Here's what the color spacing looks like in HV. Here's the color spacing in YCC, and then here is the lab color space. And as you can see, we ran all those color spacings at once in real time. So we took the RGB and we converted it into 3 other color spaces, and then we presented all 4 to be viewed by the video. Now, if we come over here, there's a couple of things I want us to look at. The input speed of the video was at 30 frames per second. So we have that. And we could see that all this was processed on the Raspberry Pi's GPU at 4 FPS, or actually more than 4 FPS, which is pretty darn good if you think about a system and so forth, and doing all that type of work. So with that said, let us go in and take a look at the code itself. And so we can get an idea of what's going on. So I'm going to open up, and I'm going to take my thing, and I'm going to go, okay, well, I'm going to open here. And so what we can do is see, I probably should have done it at another level. I'll have to open up again. So let's just talk about the application. The application has basically a main which controls the flow. And what we do with the main is we get our file video service, that's part of our Edge IQ, and our streamer, which is the output phase. And what we're going to do is on the main, we just go ahead and run through the system. We color space it. We do our FPS, and then what we do is we want to make sure that we show all forms. And so we spend a lot of time combining up using the NumPy, HStacks, and VStacks to show the video. So there's not a lot going on in the main. Most of the stuff's up here in an object that we're going to take a look at. And how we control it, if we want to take a look on it just without CUDA, we can do this. If we want, there's the file too. So if we want to change the input file, we just change it there in the application. Now let's go up to where the real work is done. So basically, let me tell you something about OpenCV as we start out. So OpenCV, when you're running and you're getting a return from their API, what it likes to do is it likes to create the variable in runtime and then destroy it. So what you end up doing a lot of in OpenCV is creating memory and destroying memory. And if you want to get a kicker, whether it's on the CPU and GPU, what you need to do is actually create the memory space ahead of time. And so that's what we spend the time on this first part, is initialization. So what we're doing is initializing the memory. And we also play a little trick to get this. We have the self.initialize, because a lot of times in your video, either video file or your camera stream, you don't necessarily always know what the input size is going to be of that video stream. So we play a little game of whether it's initialized or not. So as we come in and we look at the main core here, we're going to ask and check to see if that parameter has been set to initialize. So once we get that first frame, what we're able to do is go through and then preset, we get the shape and so forth in this initialized color space. And we then, this would be for our CPU side, we set up the memory using NumPy arrays and empty NumPy array and so forth to do that. If it's CUDA, and this gets very interesting in CUDA, we go ahead and set up the memory, and this is the memory that the GPU is going to use. So we set it up in a special format. So a lot of times when we're working with OpenCV, we work with NumPy, and we don't, if we're not C coders and we're Python coders, like most of us are, we don't actually get into the data side. So everything's done in NumPy, and NumPy has a very easy way of manipulating arrays and so forth. But if you're a C++ coder, you know that you have a data designed for CPU use called MAT, and then MAT is automatically translated over to NumPy for you. But if you're C++, you have to deal with MAT, setting up MAT variables. Well, unfortunately, when you're dealing with CUDA, you got to kind of deal the same way as you do if you're doing C++. So in this case, you do have to use this CUDA mat format here to set everything up on it. So what you're doing here is you're allocating the rows, you're allocating the columns, and then you put a variable to, or what type of system is it, or what type of memory are you going to use here, and define the variable. So in this case, I'm saying I have 3 channels because it's color, right? Red, green, blue, or whatever, YCC if it's another one. So my variables here are an unsigned int with 3 channels to it. So if I was working in, say, grayscale, I'd only have 1 channel as I set it up. And how I allocate that memory is through something called the CUDA GPU map. And I'll show you where, I'll put it in the chat section in just a second when I'm walking through this, of where you can find out information on this API and so forth. So again, I use this, I set up my GPU mat, which is setting up memory space for the GPU. Next thing I'm going to get down to is the actual color spacing work. And what I do, we talked about it, is on my first frame, I'm going to go through an initialization and set up all those memory variables. So once I get the frame, I'm going to understand the rows and the height and everything else like that. Well, rows and height are the same thing, but rows and columns. And I'm going to go ahead and get that all initialized. And then I have two paths I'm going to go through. So if CUDA is true, I'm going to go down this path. And let's start to talk about what happens here. So I'm going to take this block of code and we'll take a look at it from kernels and host to device and so forth. So let me stop sharing here. And Lizzie, can we go back to the slideshow here real quick? So next slide down, please. So if we look up one more, you're going to give away what we're going to do on contours. So anyway, as we go into this, the first thing is we have to upload the frame to the GPU. So the first thing you're going to do, now we define this at this particular CUDA BGR frame in the GPU memory. And so what we're going to do is take the one coming from the host, the CPU, and we're going to asynchronously copy that up to the host. So it's going to go ahead and it's going to copy it up as a kernel work and do that. The next thing we're going to do is we're going to change the color space. So we're going to take this system and we're going to take the BGR frame and we're going to convert it here using the CUDA instead of the regular one. We're going to convert it on the GPU. And of course, we have our stream that we've set up, our CUDA stream, and that we pre-allocated up on it. I'll point that out when we come back to the code where that's at. But we've initialized our CUDA stream, and our CUDA stream allows us then to start working on kernels. So this is one kernel. This is another kernel of work moving to another color space. This is another. So this is where we're getting, a lot of our concurrency, and we're using our parallelism of kernels to go down and do that color spacing on all the stuff. Then the next thing is, after we've done work, we have to get it off the GPU and back to the host system. So again, we're using streams so that we can asynchronously copy everything. Now, because I want the same thing to show up on the same space on each one of the videos, what I'm going to do next is really a blocking call. So as I'm downloading, I'm going to wait for all the kernels and everything to, not very good English down here, but on what explaining. But anyway, what we're going to do is we're going to wait until all the kernels finish and all the copies have finished. And so I'm syncing that stream. Even though the others may be coming down through the thing asynchronously as they come in, but I'm going to block to get that one load of code in, and I'm going to get that system, and then I'm going to present it, and then the other's going to flow down. If you're batching, a lot of times, if you're doing batch processing in CUDA and things like that, and you don't really care about real time, you can make your block up on the front as you're coming in. And so forth. And then you can also, in batching, you can start to interleave different things and so forth, and you can get more concurrency and so forth in CUDA. But we're doing stuff in real time, so we're going to block at the end of our stuff to make sure we have the 3 frames we want on it. Okay, I'm going to go back to sharing my screen. And hopefully we're back in desktop 2 land now. And so there we go back down. If we don't follow, and so if we look up here, I just wanted to show you the one thing. So on this thing here, we initialize the CUDA stream piece on it. So that's part of the initialization. I want you to see that. If you're not going to go down CUDA, if you have CUDA no and you're running on a CPU-based system, then you're just following the traditional thing. But you are going to get that pickup of speed because you've pre-allocated your memory and so forth. And then just come in, and like I said, all this stuff is about displaying a video. Now, with all that said, let's see if we actually get a pickup from our CUDA system, right? So what we're going to do is, well, first of all, I shouldn't have closed the code down because we're not going to use CUDA. So let me go ahead and reopen this on it, because what I have to do is what I was showing you is I have to make a code change. So right now, down in my application itself, I say, well, CUDA false. Well, we want CUDA to be true. This way I'll actually demonstrate something. All right, so we have that as true. and then I'll come back. And what we'll do right now is we'll go ahead. So we had before a targeted system of the Raspberry Pi. So let us go in and let's go ahead and target now our Nano device. So how do we do that? We have to run the configuration again. And what we're going to do is we're going to target our remote device here. And this time it's going to be the Nano. So we come in, we choose that. It's going to update all the token system we have. It's going to check the permissions, all the fun stuff we did before. So the good news is the OpenCV and everything, the container we have on here is CUDA aware. Good thing for me, because that's what I want to demo. And we'll go ahead and do the install. And like I said, you may see if you're running this for the first time, you may have to build out and draw down your image, but I've already done that. So that keep it brief. So then we'll start it. And let me go ahead. I just like to see it load. It's got to load that GPU up. Come on, load. Okay, so here we come in, and now this time, I'm going to miss it. We'll probably have to run it again, but anyway, so we're going to have to, but anyway, there you can start to go see it running on the GPU. I'm going to run it one more time because I did some finger fumbles there. And we'll go ahead and see, there you go. You can see it's faster just visually and so forth as it runs onto the GPU in this case. And there we see more of it and go through. So just how much faster. So if we take a look at it, we've moved from a little bit over 4 FPS to a little bit over 14 FPS. And so you can see you get, quite a boost from using CUDA and that GPU system. So that's the intro one. Take a look at the code and so forth if you're interested in using the CUDA and so forth. But now let's move in and let's take a look at something that's more interesting and developing an application that's just purely classical computer vision, and that's looking at background, subtraction, and contours. So let's go ahead and let me see where my controls are. Sorry, it's been a while. I need to find my controls. Stop sharing. Okay, there we go. Don't panic, Steve. Just press the button. So anyway, so let's go ahead, Lizzie, and launch those slides again. All right, so let's talk about, so we were talking before about, we don't have bounding boxes in the traditional sense of coming out like we do in machine learning, or a bounding box in the mask if we're using instant segmentation or something like that. So contours give us a really good thing to use. And what is the contour? Basically, just think of it as an outline of the object. Now, if you can see down here, we have the people outlined and so forth on this. And that's all using the contour functions. Well, OpenCV and Edge IQ have some really nice functions to use. So first of all, in OpenCV, when you have an image, and remember, it has to be a grayscale image. When you input a grayscale image into it, you can call their fine contours, and it will give you a set of raw contours, which has some hierarchical information as well, contour information to it. Once you get those raw contours from OpenCV, you can then use Edge IQ. And what Edge IQ can do is just give you the contours that can be used and consumed by other software, such as the one below it, which is OpenCV's draw contours, and that's how we draw these on these people. Another thing that's really interesting is you can get the moments. If I was doing physics, what are moments? Are kind of the center of gravity of an object and so forth. Similar type of concept mathematically on contour features. But what's interesting about the moments is using Edge IQ, we can put the contours and get moments, but actually what we're doing is it's probably mislabeled, and I may have to change that. Well, I'm not going to change the API because we have it out there. But anyway, what we're really doing with that API is not getting the moments necessarily, but processing the moments to get the centroid. And that centroid is this green dot. So why is that important? Well, that really gives me where that contour is in space. So I can do things, let's say, if I do an application where you're counting cars or something like that, I can find where that center of the car is. So if it crosses the line, then it's counted. If it doesn't, it's not counted, and so forth. So we can get the centroids out of that, and we can do some interesting things. So the other thing you may want to know is if we look internally on a contour, what we can do is we can get, the area of the contour. But let's say you're in love with bounding boxes. What we can do with the bounding box information, what we can do is we can use contours to get bounding box information. So not just the outline, we can put them into a bounding box if we want to, and so forth. And so and we can use an edge IQ function to get those bounding boxes from just the raw contours. So next slide. So one of the ones I find, whoops, back up again there, Lizzie. There we go. So one of the interesting things you can do with contours that I find fascinating, and I can tell you where we apply this. So what you can do with traditional computer vision algorithms is you can locate and find barcodes. So one of the great things, though, about a barcode is not one of the great, one of the interesting things about the barcode is you can have a rotated rectangle and so forth on it, or a bounding box. So with contours, what's great with OpenCV is you can actually get that rotated bounding box. It's also good for elevated cameras too, where you can have it at an angle and you can see people as they move out from the top part, they'll be rotated also. But again, getting back to the point, you can use OpenCV to get with contours to get those bounded boxes, and you really do it by getting a minimal rectangle, and that minimal rectangle has different properties than, say, a standard rectangle, and what it has is really where's the center of the system as one of its output parameters, but also as width and height. But then you have the angle of rotation, and the good people at OpenCV, they also give you, well, if you get something like that, how do I get my traditional box points that may be rotated? They have an API for that called box points. And you just simply slide that rectangle in. And if you look at the bottom one, that's the process you would go through. Because this is going to have some floating points in it, you're going to want to cast here at the end to get your box to draw it correctly, because the draw contours wants ints, not floats, and so you can cast with NumPy on that. You'll see some people will use an int 0. I'd recommend the int 8. The int 0 is something that's deprecated in NumPy. So. Next slide, please. So what we're going to do in this next one too, and this is a very useful piece of traditional computer vision. It's something called background subtraction. And background subtraction is interesting from the perspective of again, it's going to be finding objects and objects that are moving against the background. So without using, like I said, a lot of very complicated algorithms. So what it does is you have a stationary camera. The camera needs to be stationary, and you create a background model from that. And what background subtraction looks for is it then looks for changes. So in our case, we have this nice little background of the water and a little bit of a wharf, and then all of a sudden a boat comes into it, and the boat is moving along. So with background subtraction, what you have is a model, and then you subtract and create a mask, what they call foreground mask, which is a binary mask of the changes from the background model to the current frame. And so as you can see, we come out and we're going to identify the boat. And then you could start to get an idea going, wow, that's really neat. I can set it up over the top of the freeway and count cars. I can do all kinds of interesting things with it. And then you'll probably figure out we can draw contours around this. And then that will give us even more information about what's going in on that system. So next slide, please. Okay. Let's go ahead. We can come back to this. This is really around our API. And what I'm going to do right now is we'll go into our second code block and we'll start to talk about it. So let me go ahead and share my screen again. You won't see anything right now but my desktop. So what I'm going to do now is move into that background subtraction site. And so what I'm going to do is well, I should go into the background subtraction. Well, it's background subtraction, of course it's called. And we'll do the same thing. We're going to go ahead and we're going to, let me get this up here too, because I'm going to make a switch real quick. Well, that probably wasn't the best idea. All right, so what we have right now is we're going to go ahead and do our app configure again, and we're going to target our pi. We're going to pick on our pi again. So we're going to go ahead and we're going to target the pi, and we'll create a new project. And for consistency, I'll call it Hacky BS, Hacky BS, background subtraction. And again, it's an empty app because we have it there. And we have our remote device that we're going to target. Create the Docker file. And so we're going to go in and we'll hit our Raspberry Pi to begin with.
Steve, we can't see your screen.
Well, there you go. So the good news is I'm just running through configuring the application and so forth like I did before. I thank everybody for telling me that. I have actually done Hacky Hours without sharing, which is so what I've basically done right now is just configured this application to target the Raspberry Pi. And so then I'm going to install the application to it. And I actually should check out our application and make sure I'm not targeting CUDA. And so let me go back into this. I'm going to add my folder. So let me go back into Hacky here and go into this and we'll go into background subtraction. So let's go ahead and let me make sure our API is okay here. Lots of welcome screen. So anyway, so let me make sure down in the application, good, we're not targeting CUDA. I am going to show it in color. Well, I'll show it in black and white, and then we'll show it in color on the second one. So we're going to look at a pure background subtractor on this one. So we've installed the application. We're going to do an alwaysAI app start. We're going to start the application. We'll get up our Raspberry Pi 4. Started, probably started on me already. So we're coming in at 10 frames per second on this one. So this is background subtraction at work. And so what we're doing is we're picking up the people as they're moving in the background. So, and as you can see, this is running on the CPU. It's running pretty good. We had a little bit of a hiccup. I'm going to say that's probably a Wi-Fi. But that's, anyway, so that's the people, and this is the raw one. So let me kind of show you what it looks like. And again, we're coming in at 10 FPS on this one, so it's a little bit more manageable. What's nice is the application itself, even on the CPU, is running about 10 frames application, meaning Raspberry Pi is pretty good for running these type of applications. If you put it up beyond 15 FPS, it starts to struggle a little bit, where the CUDA system will just purr. So what I want to do here is I'll show you what it looks like in color. And so what I'm going to do is not do that. That's color spacing. That has nothing to do with what we're doing. So I'm going to come back and do this one and just say, let's take a look at it in color so you can see the contour piece of it at work. And then we'll walk the code and then turn loose our GPU one. So we've saved the application. We've made a change to it, and we'll app install it. So background subtraction, and we're using what they call multiple gradients. So your MOG2 algorithm is what we're using. There's all kinds of white papers up there. And we'll go ahead and we'll do an app start. And so this is what it looks like in color, so you can get an idea of what's going on. And what we're doing is we're showing the centroids as it moves around. And of course, there needs to be tuning on this system because you'll see multiple centroids. And that's just because the contours aren't continuous. And there are parameters to tune and so forth on thresholding and so forth. And we'll get through that. But that's that application. So we'll go ahead. It's kind of boring. But those are people walking around being tracked and showing the contours on them. So let's go into the code for a second here. And I think this is the, I seem to want to go back and show you color spacing all the time. So anyway, let's go into the application. So if we look at it again, we're going to have our main function, and we can turn CUDA on or off or color it on and off with this one. So with that, again, it's going to load and use a streamer using our Edge IQ, and there's a lot of information up on our site on how to use these APIs, and as well as on our training. This is just going to give me my threads per second. You know, how fast is that video coming in on it, the frames per second. That's how we're picking up the 10 and the 30. So then I'm going to go ahead and loop this thing, bring it in, and the first thing I'm going to do is I'm going to pre-process the image. And so I have two paths again through that, a CUDA and non-CUDA. And again, I'm going to be allocating my memory here through an initialization, through getting the frame, actually not through initialization this time, but through getting the frame and so forth. And as that comes in, go ahead and fill out the variables using the rows and columns and what I know about it. So this is a pretty standard workflow for using traditional computer vision. So the first thing I'm going to want to do is go ahead and blur this using what they call Gaussian Blur. Gaussian Blur basically takes what we call a kernel, and it uses this little kernel to go across the matrix and so forth and normalize the colors. So what it does is if you have a 5x5 kernel, think of a 5x5 kernel surrounding your main pixel. And what it will do is average that. And it weights the average on the Gaussian so that pixels closer to the center pixel get more weight than pixels farther away. But what it will do is normalize that color and blur it. And what is blurring doing? Well, blurring is taking out information. You don't need a lot. You don't want a lot of information as you do traditional computer vision algorithms, more or less. So this is a pretty common step of running a Gaussian blur. Now, what we can see, if you're not in CUDA, this is the standard size. So you get your frame, right? And we're going to go through and we're going to do one Gaussian blur to it, right? Well, this is a frame, but if we go down here into the CUDA, we're going to basically, where is my CUDA side? That's my CUDA side right here. Sorry, you are doing the Gaussian blur here. So you're taking your frame, you're blurring it. And then again, you're taking your frame and you're blurring it. So you're applying two blurs. What's interesting about the CUDA, when you're using any type of filtering, image filtering type of thing, you set things up first. So you set up a filter first. And so within that filter, you tell it what frame type you're going to have as your source and what frame type you're going to have as your destination frame. And then you give it your kernel size and so forth. And so you set up the filter ahead of time. And then as you move in and you're using your CUDA side of this, you come in and you drive the frame through, just as we did before. There's your CUDA stream, and we apply it. So we apply it to our source, to our destination, this filter. And then we do that again. We apply that filter a second time and so forth. So just a different workflow on that. And again, we're going to upload and download in this CUDA thing, and then we're going to wait for completion if it's going down the CUDA path. So that's on the pre-processing side. Next thing is I kind of we'll come in here and we'll take a look at what we're doing. So we get our blurred frame back. And as I said, we're using a MOG2 type of system. So what we come in and we're going to use the Edge IQ API in this case. So we have that in there for you. So we're going to use this MOG2 algorithm and we're going to process the frame. And so we want to take our blurred frame and we're going to do that. And then we'll talk about a couple concepts. We're going to talk about learning rate. Learning rate basically is how much. So you can replace the model at given periods of time and tune that if you want to. A learning rate is how many frames is it going to take to learn what that background is, right? So it's going to use to create its background model. And that parameter can move between 0 and 1, where 0 is it just takes the next frame and creates a model out of it, right? Or on the learning rate, or a background model. Or 1 is it just uses the original model it has and never changes it. So you can move it back and have that type of control, and you might need that. The other thing is the algorithm has a self-learning mechanism in it. And if you set to a negative value, I chose -1, but you put -1,000,000 in there. I wouldn't recommend that for full point, but you can put -1 or -2, whatever you want in here on a learning rate, and it will use, when it sees that negative integer, it actually has to be an integer. When it uses that negative integer, it will use an internal learning rate to that. So that's how the MOG, and that's doing the background subtraction. We'll talk about, let's move up and let's take a look at the actual API of setting that up. I should have it up here. So I just have a simple MOG process, but if I went to this one that we have going through, and I'm going to highlight it, you have a couple of parameters here. So you have the, actually, I'm going to go ahead and stop and go back to my slide because it's probably easier to talk about. So Lizzie, can we get the slide again? So let's talk these through. So anyway, we have the history piece here, and this is how many frames it goes before it changes its background model. And you may have some dynamic things that you want to do in the environment that you want to change that background around too. It could be lighting conditions that you want to change it. So dusk looks different than dawn, right? Or they probably look the same, or midday. And so forth. So you want to do that. Now, there's also a thresholding, and thresholding is how far it's called the Mahalanobis distance. So don't think Euclidean, think of correlation. So how correlated is the pixel to the background and the distance from that correlation? We've seen correlated scattergrams before. So think of the Mahalanobis distance as being the distance in a correlation. So it's seeing, before I say something's changed on my background threshold, how, I want to know how far it's varying from the background model. You can have it detect shadows too. So obviously shadows move through the thing or not detect shadows. So there's a piece in the algorithm that enables that piece too. And then, because this is used on both CPUs and GPUs, we have, whether you're gonna, CUDA, and we take care of all the setting up memory and processing and everything else for that. So we have the CUDA. We've talked about the runtime parameters. I'm not going to go back in there. So as you apply the MOG2 background subtractor, you get you have past that the learning rate is going on in that model. So we've talked about that. So let me go ahead and screen share again, and we're going to continue in, and we're going to go to our desktop once again, and we're going to share. All right, so let's go ahead, and we've seen how this runs. So let's go ahead and run it in CUDA. And spoiler alert is, because we're running at a lesser speed on the input side, the CUDA is going to perform close to the same frames per second as the CPU. But if we were to crank this up, say to 30 frames, which is normal camera input, the CUDA is going to outperform it. So you start to see the cost of using a GPU is about 15 frames per second. So where the cost benefit of the GPU really starts to kick in. So you won't see it too much here, but I did want to show you just this is how you run CUDA. We'll change it. Sorry, before we do that, the next thing after, well, I'll finish up the code walkthrough. I apologize. What we want to do is then we want to post-process the frame. And this post-processing is, again, something standard you're going to see, and it has the two paths. So what we're going to do is a bunch of morphographical operations. And Lila did a whole Hacky Hour on this when she made a screen background. And what we're going to do with the morphographical ones in our case is a road, a dilate, and a road. And what does that mean? So what we're going to do is we're actually going to sharpen the edges on our objects that were detected in our background subtraction. And again, this is pretty much standard in any standard computer vision application that you're going to do. Is you're going to want to blur for less information, and you're going to want to sharpen edges on the results of it. So so what you're doing here is you're going ahead, and again, it's in that filtering. So if you're going through CUDA, you just do, through the CPU, and not CUDA, you're just going to use your standard dilate and erode. And this is the amount of iterations we're going to do. We're going to dilate up, a 1 on the edges, and then we're going to go ahead and erode it back too, and so forth, to sharpen those edges. So there we go. That's how many. So we do 2 iterations on the erode, and we do 1 iteration on the dilate, and that's how you do it on the CPU. And it's pretty standard OpenCV. Again, the CUDA thing, you must first set up the filters to dilate and erode, and it's a similar type of thing. You get your kernel in here, which you've preset, and the kernel is, what's that object, and whether it's a rectangle or a cross. So if you have that centerized pixel, you can just use a crossing mechanism where you count the pixels around it, around in that kernel in a cross formation, so the ones at the edges, or you can use a full rectangle, which we're using a full rectangle on, so every pixel that surrounds it in the rectangle. The other thing I would warn you, has to be odd. Obviously, if you have something in the middle, 5 by 5 is going to give you that middle thing. Even doesn't work out well for having a centerized pixel. So you got to make sure it's odd number that you want to do on this one. And just very adjustable when you set up your structural element for your kernel pieces. So again, you set up your filters ahead of time in CUDA, so it all gets ready to go on that GPU and running those kernels as we talked about. And then what you do is then you go ahead and you execute the erode. So by the apply, you execute your streams down here on it. So I'm uploading my stream, then I'm applying my dilates, and then I'm applying my roads functions on that. And then of course I'm downloading, and I'm going to wait for that download to complete, and then I'm going to send it back to main. So that's the flow, very similar to what we did with the color spacing piece of it. So the next thing is, now that we have these nice little moving objects in our background, with our background subtractor, what we want to do is find the contours, so we can do some work on that. Like I said, draw them, put in a centeroid, and so forth. So what we're going to do first is we're going to get the raw contours, right? We're going to use Edge IQ, as we talked about in processing. We're going to get just the contours without any of the hierarchical information and so forth. We're going to get those. We're then going to, because I want to locate these bounding boxes, because I want to do some neat things with the bounding boxes to identify people using contours, I'm going to go ahead and use Edge IQ's get bounding boxes. And so then I'm going to get the bounding boxes. Now, I'm going to use the bounding boxes to isolate and identify people. And I'm going to tell you how I'm going to do this. So I have my contours, and I'm going to want to go through, and I'm going to have my bounding box here. And then for my bounding box, which is a traditional box, I'm going to get my X1, Y1 variables, my starting point, and then the width and height of that. Now, if you noticed, it will pick up all moving objects, a background subtractor. It doesn't discriminate well. So what I want to do is, my assumption is, and this is true of most of the world, that people are taller than they are wide. And it's true for the most part. So don't be rude about your friends that may not be, but for the most part, it's, you know, you're taller than you are wide. So what I'm going to do is use an aspect ratio. And that's why I wanted that bounding box, because I want to get to the aspect ratio. So now I got the aspect ratio of each one of those contours. And if it's bigger than one, if the height is bigger than the width, I'm going to draw that contour. And then basically I want to put a circle on it. So I wanted to show you, this is how moments are used within that, how I want to place a circle and get my XY. I could have used our centroid, but I did just want to make it a little bit different than using our simple centroid to show you a little bit about contour. So we're going to get back our moments that we talked about, and we want moments that are greater than 0. We don't want 0. Sometimes it does return 0 moments, believe it or not. And then what we're going to do is get our XY, our concurrent moments at the C, or our centroid CX and our centroid CY. If you want to know the area sits right here. So you can use that instead of using the OpenCV once you've broken it down, it's there. And then again, I just draw the circle. There's my parameters. I have my centroid, so I can draw my circle on it. And I just simply, I did the bounding box for this. I didn't use Edge IQ here because I just wanted you to see the OpenCV functions and what the OpenCV functions are doing with the raw contours. And that may become useful as you do things with contours. And then of course we just send it to the streamer. So now we've had all that information. Let's go ahead and see what that looks like on the device itself. So we're going to come back and we're going to retarget the contour, the Nano device on the Jetson Nano. Okay, we're going to look at our remote one. So again, we're going through the configuration, and the configuration lets me change my devices without changing my code, which is really nice. So we're going to go to the Nano. And it does all the stuff you've seen before. All right, and then we're going to do an app install.
Hey, Steve, while that's installing, we do have a question that's come in.
Okay.
I'm not sure, this one might be a little bit too involved. We'll have to take it to Discord after, but the question is, have you seen a multi-frame temporal machine learning model for scene subtraction?
I have not offhand, so I have not seen that algorithm yet.
Yeah, you know, if anyone has, then you're welcome to post about it on the Discord and we can follow up there. But that's an interesting question. And then there were some other questions, but I believe you've already answered them. Questions about how to kind of filter out noise and what the parameters were for the background model. So if you have any additional questions about that, you can post it in the chat or follow up on Discord. But for now, I think we're good. And we'll just watch the demo.
And it is important. So, I mean, if you looked at the initial raw thing without doing aspect ratio, there is a little fence, right? It's a fence, and the wind will swing it, and you would see those things in there on it. And I'll point it out when we run this one on it. But there's just a lot of fascinating things. I'll have to look into that one. I haven't seen that. That might be a much better, interesting algorithm to implement. So let me go ahead while we're getting up here on it. So here we go. As you can see, it's running about the same thing, but by doing the aspect ratio, we're not picking this up. As you can see, it moves and so forth. And then as people are walking, these things can get picked up too in there. So what we're doing on that. So like I said, you'd have to play with these contours a little bit because we are getting multiple, you know, it's discontinuous, but you can see the little green balls dumping around and so forth. So there is some tuning and so forth, but we're not picking this thing up moving. So that's nice. So we've got step one on it. So again, it's not, this one at 10 frames per second, it's not going to show any great speed to it. There, like I said, there is a cost to using the GPU, but what we've done is we've offloaded. And let's say you do have a big machine learning project going on, you want traditional computer vision. By using the CUDA piece, and OpenCV's CUDA, you're able to really offload too on those types of things. So you can let the CPU do great things like what you're working on, Lila, and what we're introducing over the course of this quarter, and that's analytics coming up and having the CPU handle pushing analytics to the cloud and so forth. So that's done, and we'll come back. So you can see it was about 9.71. So actually, in this case, just you staying on the CPU was a little bit faster for us. Came in at 10 and so forth. The overhead of the GPU kind of cost us here on it. So it's just things to do it. But if, like I said, I jammed it up to 20 frames per second, then this is gonna still hold about the same variance. It's going to be very close to that 20 frames. Threshold is going to be around 18 to 19. So anyway, there's one last thing that I'm going to do is, and I'll put these in here. So this is the OpenCV site. We're on 451. We're going to go to 454 here pretty soon. But anyway, so these are all the different functions you can take a look at. There's device layering. You can set your devices. You can do all kinds of stuff from optical flow to detections and so forth. There's all kinds of great stuff, image processing and so forth that are in there. The other thing is, as I said, you are exposed to memory operations. So let me kind of go back to the top. So you do have to worry about this GPU mat and so forth. You can get in some interesting things if you start working with gradients and so forth, like you would. They're not some of the helper functions to get you back from a float 32 to an int 8 and so forth. So you're going to have to use some of like the convert to functions and so forth. And I guess my biggest hint there is if you're working in floating point, the floating point precision is 0 to 1. Because you can do all kinds of stuff, you have a lot of precision between as opposed to when you're working in the normal space and it's 0 to 255 for a color, right? So you're going to have to scale it out back and forth as you move between those things. C coders completely used to that. Python coders maybe not so much, and maybe even you aren't in C coding because they have a lot of helper scale functions and things like that in the traditional CPU version of OpenCV. But be careful when you're moving between floats and unsigned int 8s. So on that you're going to have to do some work on that on the scalars and so forth. So I will go ahead and put these in the chat so people can take a look at those. And that's it. We're ready to jump into, well, I guess we go to the conclusion. Let me go to chat here and put those into chat. So so everyone can see these. So this is the OpenCV page. And then let me go to, this is the other one that you need to pay attention to. All right, let's go and just talk through and get the slides up there. So, so if we go down a couple, yep, we did the background. So just on the conclusion, as you can see, you can do different things using OpenCV's CUDA libraries and traditional computer vision that are really cool. One of them is, and I'm gonna get it up there, I still haven't finished it, but I'll show a barcode detector. And that's a good use case for traditional computer vision, is to detect where that barcode is using those traditional mechanisms. Smart cities, we saw it, counting cars. You can use background subtraction and so forth to count cars, count people going in and out of an event and so forth. So there's all kinds of great usages for those. There's good usages combined with the machine learning pieces. And that's our Hacky Hour.
All right. Thanks, Steve, for those demonstrations. Thank you all for sticking around to the very end and participating in today's Hacky Hour. If you're interested in seeing our product in action, our team loves to do demos. You can schedule a demo at alwaysai.co/schedule demo. And if you'd like to watch this Hacky Hour again at a later time, it'll be available on our blog, and our tutorial is available on our website. Thank you again for joining us for Hacky Hour, and we hope to see you next time.
All right. Bye, everyone.